Okay, folks, from the looks of it, from 2017, we're still looking at rumored 530 sieverts, possibly even as high as 5,000 sieverts in those reactors. Well, that's interesting because we don't know exactly how much of that radiation is coming out is from uranium decay and how much is the other ones. It's estimated in a nuclear blast from a bomb that only 5% of the radiation outputted is actually long-term radioisotopes such as iodine, cesium-134, cesium-137, and strontium-90. So basically, what are we looking at? What are we actually looking at as the baseline for the iodine, the cesium, and the strontium? And how much of that radiation is coming from the uranium? The fact that it's building upward indicates it's not coming only from the uranium. It would not be increasing. The uranium should decrease with time. That means that we're talking about strontium, cesium, and iodine in all likelihood. And the iodine I have calculated probably has capped out or topped its up to its maximum sieverts it's going to produce, which by the equation I use from that 530 sievert figure, that come up to 422.4 sieverts. That's a lot of sieverts. We don't know exactly how many of those 530 sieverts is actually coming from iodine, though. But there is an estimate available on the internet that states that it is 3%. I think I got that off of Wikipedia, if I remember correctly. You can also find strontium 90s on Wikipedia. I've not been able to find cesium-134 or cesium-137, so there's not too much I can do about either one of those as far as confirming or denying. That means that roughly about 10% just from those two, iodine and the 131 and the strontium 90, almost 10% of those 530 sieverts are probably from those two sources. And remember, first uranium has to decay, then the iodine has to decay. Or the uranium has to decay, then the cesium has to decay. Or the uranium has to decay, then the strontium has to decay. They don't all decay at the same time. It just doesn't happen that way. But once the reaction starts going, and you get a reaction going, which is the whole point of a nuclear power plant, is a continual reaction. Once that continual reaction gets started and is starting and going and continues to go like it is now, and like it happened when this accident occurred, it's now unfeathered as to what it's doing, but we're lucky and it's not concentrated enough to cause a nuclear explosion, so it's just producing a lot of radiation. Heat and radiation, thermal heat, so forth and so on. So basically this is what we're sitting at right now. We are sitting at a Fukushima where the uranium is slowly declining, but the other byproducts of the fission reaction are climbing, except for possibly iodine. Iodine looks like it's hit top, but still that's 422 sieverts right there alone. Then you got cesium and strontium as two other major players. I mean, if the estimate that goes to 5,000 at the core in sieverts, and they haven't positively identified it was, they only positively identified 530 outside the building. That's a lot of sieverts. Well, Thomas Wills here. Have a good one.